A doctor prescribes 275 milligrams of a therapeutic drug that decays by about 35% each hour. Write an exponential model representing the amount of the drug remaining in the patient's system after T hours. Find the amount of drug that would remain in the patient's system after 4 hours. Round to the nearest milligram. Okay, since we know the percent that's reducing each hour, there's kind of a shortcut way of answering these types of questions, which is kind of cool. So we can basically say the amount that's in the bloodstream after T hours is going to be the initial amount, so 275, and then you multiply that by a percentage change over time. Now, if you want no change, you just multiply it by 1. You just leave it at 275. If you want it to increase, like if it increases by 5% per hour, kind of like with a bank account, you make the multiplier 1.05. But if it's decreasing, you take 1 minus whatever that decreased amount is. So we could say this is 1 minus 0.35 to the t. So we can easily say this is 275 times 0.65 to the t. And that's a great exponential model for this principle. So the amount that's left over after, let's see, it was 3.5 hours or 4 hours. Yeah. So the amount left over after 4 hours, 275 times 0.65 to the 4th power. And using the calculator, let's see what we come up with. So 275 times 0.65 raised to the 4th gives us about 49, 49 milligrams. I believe it was milligrams. Yeah, it was in milligrams, not grams. Okay, another way, which is a little bit more in line with how most textbooks would approach this, but certainly a bit more difficult in my opinion, is to use the standard growth model, which is y equals y naught e to the kt. And what you need to do is you need to solve for k. All right, so you have an initial amount of 275. That's clearly the value of y naught. Then it's going to be e to the k times, it reduces 35% each hour, so let t equal 1. Then if we reduce by 35%, then effectively we would take 0.35 times, well, actually, if we reduce by 35%, we would need to do 0.65 times 275, wouldn't we? All right, so then we have 178.75. That would be the output after the first hour. All right, now we have to solve for k. So we would try and get k by itself, but we aren't going to be able to do that yet until we get the 275 out of the way. So I now have 178.75 over 275 is equal to e to the k. So this is in exponential form, and in order to solve it, we need to change to log form. So it would be a log base e of 178.75 over 275 is equal to k. And of course, a log base e is just a natural logarithm, so we would use a natural logarithm in the calculator. And let's take a look at what happens. So we get the natural log of 178.75 divided by 275, and that gives us a value of k of negative 0.4309, we'll say. So k equals negative 0.4309. So then our model would be a of t equals 275 e to the negative 0.4309 t. And that right there is also a perfectly fine way of expressing this change. And if you want to know how much changes after 4 hours, so what amount of the drug remains after 4 hours, well, you would just plug that into this formula. So you would do 275 times e to the negative 0.4309 times 4. And I missed an exponent here, sorry. So raised to, and then parentheses, there we are. Okay, and we get the same answer, 49. So there's still 49 milligrams remaining. So either way works fine, but I think you can tell that there's a clear winner here. The only problem with the first method is that it only actually works under certain conditions. Here we knew the percentage decrease per unit time. And that's the important thing to know. If you don't know the unit increase or decrease per unit time, then you have to resort to the more general method, which is the second process. So both are definitely worth knowing.